All right, good day. Welcome to today's class. We're going to take a look at circle geometry. We'll take a run through about 8 circle theorems, how they're applicable to problem solving. Now let's get started with our slides right away. Okay, we're looking at circle theorem. We're looking at circle theorems. Now the first thing we want to look at is the various part of a circle, which I believe we should be acquainted to. The radius, we have the diameter, we have a line that is drawn to intersect the circle at a point. That line is called a tangent. We have a chord. A chord is a line that is drawn to intersect the circle at 2 points. The line that intersects the circle at 2 points, that is drawn inside the circle to intersect at 2 points. That is a chord. Wide diameter is a special kind of chord anyway. So we have sectors, we have segments of a circle, and so on. Now let's move straight to our first theorem. The first theorem, theorem number 1, it says that the angle at the center of a circle is twice the angle at the circumference. The angle at the center of a circle is twice the angle at the circumference. Just a moment, please. All right, now if you have an angle at the center of a circle in this kind of diagram, the diagram shows an arrow kind of quadrilateral in a circle. That arrow, we call it arrow diagram, or diagram, we call it arrow diagram. So if you see an arrow diagram in a circle where the vertices touch the circle in this manner, you have that the angle at the circumference here in blue is going to be 2 times of it that you have at the center here. That is for theorem 1. Then let's go to various forms of that theorem 1. Theorem 1 can have various forms, which we'll talk about much later. So we have these as the various forms. We have this one. Okay, we have this one, we have this one, we have this one, and then move this away. And then we have this one. There are the 4 forms. They are the forms which theorem 1 can take for diagrams. Now let's move to the next theorem. Let's move to the next theorem. Theorem number 2, angle in a semicircle. Angle in a semicircle. Angle in a semicircle is a right angle. If you see a diameter in a circle which extends to becoming a triangle, the angle subtended at the circumference right here is going to be 90 degrees. And the reason we will quote when we are using the theorem in problem solving is angle in a semicircle. Angle in a semicircle. Of course, you know that the angle at this center here is 180 degrees. So angle here is 180. Then half of it is going to be angle at the circumference there. Take note, for you to use angle in a semicircle theorem, you must have this point on the circumference of the circle and subtended by the diameter which you have in the circle. Theorem number 3, we have angle in the same segment are equal. Angle here and angle here are equal. Angle here in blue and the one here in blue are also equal. For you to use this theorem, you must be seeing something that looks like a bow tie. You must see something that looks like a bow tie in the circle. So we have this bow tie diagram in the circle. And take note that the bow tie diagram has its vertices. This point has vertices, all 4 vertices on the circumference. This on the circumference, this on the body of the circle, this on the body of the circle, and this on the body of the circle. All 4 vertices must be on the body of the circle. So take note of that. That is a condition for which you can use the angle in the same segment theorem. when you use this theorem in solving problem, you just simply say angle in the same segment. That will do. Theorem number 4. Theorem number 4, we have a cyclic quadrilateral. The theorem says opposite angles of a cyclic quadrilateral add up to 180 degrees. It means that if you have a four-sided plane shape inside a circle, such a way that the vertices, once again, the vertices, that is this point, this point, this point, and this point are on the circumference of the circle, then you claim that that is a cyclic quadrilateral. If you don't have that place, you cannot refer to that quadrilateral as a cyclic quadrilateral. It is not possible to use the theorem. All right, so this angle here in blue and this one here in blue, they are not equal. They add together to give you 180. So B plus D equals 180. Likewise, C plus A equals 180. Reason, opposite angles of a cyclic quadrilateral. Now let's go to the next theorem, theorem number 5. Theorem number 5. Theorem number 5, okay, before theorem number 5, we have a problem here that you might want to take a look at. You have a cyclic quadrilateral here. You also have a bow tie, about 2 bow tie, whichever way you want to see it. You have bow tie diagram here, so you can make an attempt to get this problem solved. So straight away to theorem number 5, it says angle between a tangent and angle between a tangent and radius is a right angle. You can see this line drawn to touch the circle at this point. If a line is drawn to touch a circle at a point, a single point, we call that line a tangent. You have this line drawn from the center of the circle to intersect the tangent. That line is called a radius. If a tangent and a radius meet, what you have formed is a right angle. So that's a right angle you have there. We can have in problem given to us this diagram as complete triangle. We'll look at various forms where we can have this theorem used as we go on in the other theorems, and some problems we may look at later. So please take note of this particular theorem. It is very easy and simple to identify when it comes to use in problems given to us. Now the next we have theorem number 6. Tangents drawn from a point. This is a point where the two tangents are drawn from. This tangent and this one, they are drawn from this particular point to the circle. So they are drawn to meet the circle at this point and at this point, which means that the two tangents are equal. So you can see the dash here and the dash here, indicating that both lines are equal. The dash may not be there when you have questions given to you, but you just have to know that the theorem applies when you see two tangents drawn from a particular point, such as this, to the circle. Take note, the tangent is not the line that is drawn from here to this point. No, the tangent is from here to this point. Likewise, from here to that point. So that's what you talk about as being equal. So even if this one is extended beyond this point, we are not interested in that. We're interested in where it was drawn from to where it touches the circle. Now you can see that this is a radius. If it's a radius, then you have a right angle formed there. So we have tangent and radius theorem applying also. Now take note, it is possible to have a problem given to you in such a way that you have a line extending from here down to this point, so that you have a triangle. Now that triangle shows a radius, shows this radius, and this chord as an isosceles triangle. So we have an isosceles triangle there. Mind you, the bigger triangle here, but formed by this tangent and this tangent, also gives us an isosceles triangle. So we have the angle at this point and the angle at this point to also be equal. So we have two isosceles triangles, the big one and then this small one. So you can take note of that when you are solving a problem. Now let's move to the next theorem, theorem number 7. Theorem number 7 says the angle between a tangent and a chord is equal to the angle at the circumference in the alternate segment. Well, simply put, we say angle in alternate segments. Now, when do you make use of this theorem? When do you make use of this theorem? You make use of the theorem when you have you make use of the theorem when you have a tangent drawn and a triangle sitting on the tangent. You can see the triangle sitting on the tangent. Take note also that the triangle has its 3 vertices touching the circumference of the circle. If this is not the case, then we don't make use of the theorem. Number 1, a tangent must be there. 2, triangle sitting on the tangent. 3, all vertices of the triangle. All vertices of the triangle, I mean, this point of the triangle must be on the circle. This point of the triangle must be on the circle. And the third point, of course, will be on the tangent and on the circle. Otherwise, you don't use this theorem. So we have that this angle, so I particularly make my students to understand the use of this theorem in simple way by saying, when you have this diagram, the angle between the chord, this angle here, for instance, and the tangent, draw it. Now, instead of continuing like that, no, I'll tell them skip that part which I just drew now. This drawing, I'll do it again. Don't draw that, skip it, skip that part, then move up the line, move along the line and go up. So that angle you have there, is the one that is equal to where you are coming from right here. Now let's take a look at the other one. This angle here between the tangent and the chord, this one here, between the tangent and the chord, you draw it. You don't draw the inner one, you skip that part. So you draw, you skip, and you move along the line. So when you get up the line, the angle there on the circumference is what is equal to the one outside there. The simple statement you give as your reason is angle in alternate segments. Angle in alternate segments. Simply write angle in alternate segments. This here, angle in alternate segment. That will do. Not writing this whole long story. Angle in alternate segment, that will do. All right, that will do for theorem number 7. Where we have a problem that you might want to take a look at. This problem, but take note that this triangle is an isosceles triangle, and take note this is not 90 degrees. It's an error. It is 50 degrees from the written statement in the question. This is 50 degrees, not 90 degrees. So you might want to take a look at it. So if here is 90 degrees, then if here is 50 degrees, please, then this angle here at U is 50 degrees, meaning that here is also 50 degrees. Why is here 50 degrees? Base angles of isosceles triangle. So you can find this angle here and then get VXY. Okay, angle VXY, we are asked to solve is a combination of this angle here inside the triangle and the one outside here. So you can take a look at that. I'm sure you have no problem with that. Now, the next theorem, number 8, the perpendicular line from the center of a circle to a chord bisects the chord. The theorem states that if you have a line drawn from the center of a circle to meet the chord or a chord, that line divides the chord into 2 parts. So we have this part of the chord and this part of the chord equal in length. You might have uh, uh, a problem such as this in questions given with complete triangle like that. So you will be having two right angle triangle, or you will have an isosceles triangle in full. So you will know how to use that. I'm sure we'll come across that in our problem solving class. All right, so let us take a look at the next slide. All right, so this is an extension of the particular theorem that we're talking about in this full form where you have triangle formed. Okay, next slide. This is an extension of theorem number 1. So let's quickly take a look at theorem number 1 again. Theorem number 1 again. You have a circle. You have a circle, for example. You have a circle. Then you have this to the center of the circle. Then you have another one here to the center of the circle. We'll consider these two as permanent lines that are hanging at the center of the circle. All right, from what we have looked at so far in the first theorem, in theorem number 1, you have a line like that, and you have another one like that. So you have the angle at center is twice angle at circumference. But if this line, let's say we have not that line in that manner, let's say we have both lines, in this manner, which I'm going to draw right now. Instead of this line to just hang there, somewhere there, and the other one following, it decided not to hang there, but it moves so that it lies on the first line, so that the other line also does not, but it just follows its own pattern. So we have a diagram looking like this. So this is what we talk about as the extension of the theorem number 1. So take note, in this case, we still have that the angle at this center here is 2 times of the angle here at the circumference. So theorem number 1 applies. But you can also have another extension of that particular, okay, as our diagram is done. We have to do another diagram. What if you have of course, that's not it. Okay, so I'll line again. Now, in the case where you have that line that should run like that gave us the last diagram we had. Instead of running like that, it decided to cross over and cross to this place. So it's the same theorem that applies in this case also. So we have another form of diagram for that particular theorem number 1. So it's still the same case. Angle at this center is 2 times angle at this circumference here. The angle at this circumference there. 2 times angle at that circumference there. So take note of that. All right, so that does it on this particular. Okay, we still have one more. We have one more. We have the case where instead of this line running like that, running like this, running like that, or running across that way, instead it falls down this way in that manner. And we have another one running like that. But in this case, it is the angle that is right here. The angle that is right here, that is twice what you have here. So angle at this center, which is the reflex angle, is 2 times what you have at this circumference right here. So this is the last form of the diagram which the theorem 1 applies to. All right, so that would be all for this. Now let's go to the other problems that we have to show. Okay, we have some problems down there. You can take a look at them. You can pause the video and take a look at them. All right, we have some down here. Angular center, we apply angular center is twice angular circumference. Angle in a semicircle. Angular center is twice angular circumference. Angles, opposite angle is side quadrilateral. Angular center is twice angular circumference. Angle in a semicircle, and then sum of angles in a straight line. Also, you have angle, exterior angle of a triangle also applying in that particular case. Okay, let's go to the next slide. All right, we have more problems here, and here we have bow tie, angle in same segment applying there. We have a cyclic quadrilateral, 2 of them. There we have another bow tie diagram, angle in same segment. Angle at center is twice angle and circumference. We have a bow tie diagram here. We have a cyclic quadrilateral here. All right, so these are problems you might want to attempt on your own. All right, so we are done with this particular one. Let's go to the next slide. All right, so here we have 2 lines. Take note that these 2 lines are, this one here and this one here are parallel lines, which implies that you have angle between lines that are angle between lines formed when you have parallel lines and a transversal. So take note, this line, if it's this line, let's go back. Okay, you have a line like that, you have another line like that, and 2 lines are parallel. Then you have another one running across in that manner. So you will have the case of this angle here. You have the case of this angle here, and this angle here as corresponding angles. Corresponding angles are equal, so which means that this angle here is equal to the angle that is here, corresponding angles. Mind you, the angle here, the angle between this chord and this tangent here, the angle here is equal to the angle here. Remember, I said, sorry about that, I have to erase that. It's equal to the angle here. Remember, we said draw. So if you draw this, then you skip the one inside and then move up the line, that angle there is what is equal to the one outside there. So that is for this particular problem. So you can take a look at it and attempt solving it. All right, we have another. This is not a cyclic quadrilateral. Take note, this is not a cyclic quadrilateral because this vertex here at O is not on the circumference of the circle. We have 3 vertices on the circumference, but the 4th one is not on the circumference of the circle, so this is not a cyclic quadrilateral. Also note that this and this angle form angle on a straight line, so you can use angle on a straight line to get this particular angle here. Then when you get the angle there, you can get the angle here at the center, which is the reflex angle, POR. So that angle there will be 2 times of what you have right here. So that is for this problem. Let's go to the next slide. All right, take note that this line TS, TR, and PR, they are not tangents because they are touching the circle at more than 1 point. So they are not tangents. It's supposed to touch the circle at just a point inside the circle. Not outside the circle, I mean, not inside the circle. Even if this line were drawn and touched the circle at this point and not extended, if you extend the line, it will go into the circle and touch at another point. So a line that touches circle at a single point outside the circle is the one that we refer to as a tangent. If you extend the line and doesn't touch it in more than one point, it is a tangent. Next. All right, this is a problem you can also look at. This is not angle in a semicircle, no, because this triangle does not have its third vertex here, which is here on the circumference. So take note of that. But you know that this is a radius, OR is a radius, OP is also a radius, so isosceles triangle. You can find this angle here at this spot, then be able to find this angle here and this one here because they are base angles of isosceles triangle. Next. All right, take note. This line is not a tangent. Line PR is not a tangent, but line PQ is a tangent. When you extend this line further, it still remains as touching the circle at a single point. All right, take note of this line QR. If you extend it, it goes and touches the circle at this point here. If you extend that line, it goes touching the circle at that point there. So it is not a tangent. It's not a tangent. It's not a tangent. Take note of that. It is not a tangent. This is a tangent. SR is a tangent. Take note of that. SR is a tangent. And mind you, you'll notice that in this particular question, 79 degrees is given down here in the statement, but it's not in the diagram. So when you are solving, you will actually merge all that is written in the statement with the diagram, and then you have your answer right away. Now the next slide, let's see. Okay, this is another problem. You can take a look at that. All right, that is the end of our lesson. Once again, thank you for watching. In the next class, we will be looking at some problems, application. In the next class, we'll be looking at the application of some problems. We'll be looking at the application of the theorems in solving some problems. Thank you for watching.